guys, welcome back to 100 Days Machine Learning Crash Course. Today we want to see an example of how to build models in Keras. Okay, so to see the example, we want to work on MNIST dataset. Okay, so the MNIST dataset has some images from different numbers, and we want to recognize these numbers. Okay, and for this we want to create a CNN to do that. Okay, so to build this network, the MNIST images are 28 by 28 gray images, so we have just one channel because this is not an colorful image, and so we just have one channel. Okay, so we want to first apply, let's say, 32 filters. So now we are designing our CNN architecture. It is highly recommended to, if you are novice in this area, you find a paper that has an architecture suitable for your task and then implement that. So, but the MNIST dataset is so simple, so we just creating a simple architecture design for this dataset. Okay, so in the first layer, we want to have 32 filters, and the size of filters are 3 by 3. So after applying 32 filters, we end up with 32 activation maps, or 32 channels in the next layer. After that, we want to apply 64 filters, also 3 by 3, and so let's say we have 64 channels in the next layer, and then we apply max pooling to a 2 by 2 max pooling to reduce the spatial size of the activation maps. And after that, we use a flatten layer to just vectorize these activation maps, and use another dense layer in here. After that, we use a 10 output for our numbers. Okay, so this is the last layer with softmax activation function to get the probability of the output. Okay, so let's build this with Keras. Okay, so we want to go through this example in Keras and learn how to use Keras to build that model. So first, let's import some necessary packages like NumPy, and let's import matplotlib to plot some of the images. And from, if you want to use, in here we have dense layer, we have flatten layer to vectorize these activation maps, we have convolutional layers, and we have the input layer, so we should import them in here. Okay, so we want dense layer, you could use tab key to see the choices for auto completion, and we want the flatten layer and input layer, and also max pooling 2D. Okay. Okay, now from datasets, we want to work on MNIST, and we want to show some random images. So from random we import randint, and to build the model we need to import model from models, and we want to use optimizer. You could import them from Keras.optimizers. We could import SGD or stochastic gradient descent or RMS prop or Adam or other optimizers like Ada Delta or Ada Grad. Okay, so we will use Adam for this task, and we also want to categorical. We will see that why we should import that, and also from Keras.callbacks we import model checkpoint and tensor board. We will see either we will see why this is also useful for us. Okay, so the first step is to load the MNIST dataset. So the loading is pretty simple. So we just have a two partition dataset for MNIST. One partition is train and one partition for test. So we use MNIST.loadData method to load the dataset. Okay, now we could print xtrain.shape to know how many training images we have. Okay, this is why train. Okay, so now we could see that we have 60,000 images for training, and the images are 28 by 28, and also so we have 60,000 labels for these images. Okay, and just note that in Keras you should pass the images should have this shape. So the first thing should be the batch size or number of images, or you could interpret that as batch size. The next thing is the width of your image, and then the height of your image, and at last you have number of channels. So in the case of we have grayscale image, we have one in here. Okay, so we have 60,000 training images. Let's see some of them. To see some of them, we create a loop. Let's see 100 of them randomly. We create random numbers from 0 to 60,000, and also we want to print the label of the digit, and now we want to show the nth image with matplotlib, and okay, let's just run that. Okay, now you could see some examples of the dataset. So for 9 we have this image, for 7 we have this one, So this is for 2, and as you could see, we have some noises in the image. And so these are the examples of the MNIST dataset. Okay. Okay. Now let's move on to continue our example. After loading the dataset, we should change the type of the training data to float 32 in order to be able to normalize the training data and so on. So for both training data and test data, we should convert them to float 32. And this is important because if you are reading images and you want to normalize them, the images by default, if you are working with OpenCV, for example, they are uint 8. So when you divided them by 255, then the result will be 0 or 1. Okay, but we want to have floating divisions, like having 0.8. So before that, you should so before that, we should convert the type of the training and test data. Okay. After that, we should make the shape of this the standard shape. So we have the number of training data, which is good. We have the width and height of the image, and we need the number of channels. So we need 1 in here. Okay, so we add that one with expand dims xtrain, and we need to add that axis in the last position. So we do the same thing with test data, and now we could print the shape of training data and test data. Now we could see that the shapes are in a standard form. Now it's time to build the model. So the first layer, as you could see in here, is the input layer. So we should specify our height and width of the image. Okay, so I named it model input. So this is the first layer, and we have an input layer from Keras. We imported that layer. Okay, so we have an input layer in here, and the argument is the shape of your image. So it could be 28 by 28 by 1, okay, or height, width, and number of channels if you work with OpenCV. At first we have height, and then width, and then number of channels. Okay. After that, we have we should define a convolution layers with 32 filters, 3 by 3, and let's say we have ReLU activation function. Okay, and so let's call that layer X. So we have a convolutional layer, and we have 32 filters in that, and the kernel size of the filters is 3 by 3, and the activation function we want to be ReLU, or you could also use tangent hyperbolic, or also we could define custom activation functions. We will see those more advanced things in next sessions, and in here after, so this is the convolutional layer options and properties. Now in here you need to specify in here what is the layer that you want to connect to this layer. Okay, so in this case we want to connect model input to this layer. Okay, so we have model input. After this, let's say we could print the shape of X in here to just check the shape of this layer. So as you could see in here, when we create the model, we don't know what is the batch size. Okay, so or in other words, we could train the model with different batch sizes. And so for the model, it makes no difference to how to set the batch size. So we have an unknown in here, and we have 26 by 26 in here because we have 3 by 3 filters, and we have 28 by 28 image. So we have seen that after the convolution, we have a reduce or reduction in spatial size. If you want to have the same shape as 28 by 28, we could see that we could use the padding. We could use same, or you could use also zero padding to get the same shape. Okay, so we have 26 by 26 in here. After that, we need another layer. Again, we could call this X because we don't want to actually do anything with this layer, so we could define another layer with the same name. So we have another 2D convolution, and in here you could see that we want 64 filters. We have kernel size 3 by 3, and the activation function is relu, and the input for this model is X because the previous layer is X in here. Okay, you should note that too. Here, after this, we want to use max pulling. So we use max pulling in here with pulling size 2 by 2. So we both reduce. So if we have, let's say if we have 100 by 200, after max pulling we have 50 by 100. Okay, if we use max pulling 2 by 2. If we use 2 by 1, then we have a reduction by sampling rate 2 in one dimension, but 1 in another dimension. Okay, so we have max pulling. In here, I think it is important to say that when you are working with OpenCV, so the first argument in this is height and then width. So don't worry about it, and you don't need to change that in order to pass it to Keras. Okay, let's continue. And the input for this layer is X. Let's add maybe another convolutional layer, and the input layer of that is X again. And let's add another max pulling layer in here, and after that we need a flatten layer. So let's see the shape of the last layer in here. So we have 5 by 5 by 64 channels, which is the number of filters from previous layer. So we need to use flatten layer, and the input of this layer is X again. So if now we print that, we could see that we just have two dimensions. The first one is for batch size, which is not important. The second one is related to just unraveling the activation maps from previous layer. Okay, now we need to apply, let's say, a dense layer. We could have maybe 32 nodes with relu activation functions, and for the last layer we should use the number of classes nodes for the output layer, and the activation function should be soft max. Okay, and don't forget to specify the previous layer in here. Okay, after creating these layers, we should create a model. Let's call it model. We should use the model in here that we import to specify the inputs and the outputs of the model. So the inputs of the model is model input, as we have it in here, and the model output is X. And as you could see in here, we have outputs, so we could have some models to have multiple outputs or multiple inputs, so they are more advanced models. Okay, so now we could compile the model. Okay, and there is a good and useful method called model.summary that we could see the model architecture in here. Okay, so we have for the this is the input layer, and it doesn't have any parameter. So in the next layer we have a convolutional layer with 32 filters, and so the number of parameters for 3 by 3 filters with 32 filters, we have 320 parameters, and so on. As you could see, in the dense layers you have lots of parameters. Okay, so you should know to these dense layers, and in here you could see the total number of parameters and trainable parameters. If you wonder what is this non-trainable parameters, sometimes you may stop training some of the layers or use pre-trained network in order to extract some features. In that case, you could freeze some layers to not train in your training procedure. Okay, we will see that later. Okay, after that we need to define the optimizer and compile the model itself. So let's say the optimizer is Adam, and the learning rate is 1e minus 3, okay, which is fine for optimizers as an initial guess. Okay, and also we could pass some other parameters for optimizer Adam, but the learning rate is the most important parameter, and mostly we should specify that parameter. So we just specify this in here, and now we could use compile model to specify the loss function of the model. So the loss function is categorical cross entropy. So this is the loss function of the model. The optimizer is opt, in here we defined that, and the metrics that we want to see in the training procedure, let's say, is accuracy and also the categorical cross entropy. We could actually define custom metrics, but for now we just stick to the basics, so we don't do that in here. Okay, great. Now we should convert the training labels to the categorical labels. So now we have, let's print an example of training label. So it is 3, but we know that the output of the model is 10 neurons or 10 nodes in the output. So we should encode the output as categorical output. So when we have 3, we need to probably go that in this way. Okay, so sorry, so this way. So this is 0, 1, 2, 3, and 2, 9. So we code the numbers in this way. So the Keras has a useful function called toCategorical to do that. Okay, so we could use toCategorical and pass the training data, the number of classes, as the second parameter, and we do the same thing for test data. Now if we print again this, now you could see that we have the encoded label as categorical data. Now we could to train the model, you could use fit method. The first argument is the training data, so we need the images, the training images, and the labels. After that we need the batch size. So in here, let's say 128 or whatever you want, or let's say 64. You should actually optimize that with cross validation, but in here we just use 64, and for number of epochs we use 100 epochs, and we set the verbosity equal to 1, means that we want to get some outputs. And for validation data, we could pass that as a tuple, which is test, xtest, and ytest. And there is a useful thing in Keras which is called callback. So during the training, after each epoch, maybe you want to save the model or log the data into a file. So in this case, we could use the callbacks in Keras. We have different callbacks. Now we want to just learn about checkpoint callback, which could save the model after each epoch. So as you could see in here, we import from callbacks, we imported model checkpoint and TensorBoard. So let's create those callbacks. So we create model checkpoint callback, and the first thing is the name of the output file that you want to save your model. And so let's say it is model, and the format is H5 or HDF5, whatever you want, but I use H5 in here, and it should monitor the validation accuracy, because I just want to keep the best model. And so when the accuracy, when the validation accuracy goes up, I want to save the model after the epoch. But if the model accuracy is going down, I don't want to save the model or overwrite this model with this model. Okay. And we use the verbosity 1, means that we want to get some output, and we save the best model. And because we have validation accuracy, we need to keep the maximum accuracy or validation accuracy. If this was lost, then probably we need to use min in here. Okay, and after that there is another callback which is really useful, is TensorBoard callback, which allows us to see the graph of the loss function during the training. We will see how to see the training procedure with TensorBoard. So we just, the first argument is the directory that we want to get log. Let's say we don't want to save the images, so this is the most simplest form of that. And in here you should pass those to the callbacks argument. So we pass the checkpoint as a and TensorBoard callback as a list to the callbacks. Okay, if we run that, we will see that now the model is trained on the dataset, and we could see the metrics. As you could see, we could see the accuracy, the categorical cross entropy as the metrics, and in the training directory you could see the graph because it is logging the training procedure. Let's wait until this epoch gets finished, then we will see what is in that directory. But to just run the TensorBoard, so you should see this file with TensorBoard. Okay, this one you could not just open this file. To open that, you should open a terminal and type TensorBoard logdir, which specify the directory of your logging. Then in here we have graph. Okay, if I run that, it gives me a local address. I could open that with the browser. And now I could see very cool things about my model. So in here I could see the model itself and the optimizer and the structure of model. And now we have one epoch finished. So if we refresh this, now we have a new tab, a scalar. So in a scalar, you could see now, because we just have one epoch, we have just one point in here, but this is the accuracy, the categorical cross entropy for training data. This is the validation accuracy, and so on. So this is so cool. In the training procedure, you could, let's see when the second epoch finished, then we could see the second point will be created, and we could see the plot of those points. And you could actually save these plots and put them in your report or whatever you want to track, or use cross validation to see, or use the earlier stopping. You could track the accuracy. And also to use the earlier stopping also is a callback. So you could use earliest stopping callbacks. Keras. Actually, there are lots of callbacks in Keras. I highly recommend to read those callbacks. And as you could see in here, now we have model checkpoint in here, we have early stopping in here to use early stopping, as we have learned about what is early stopping. And also you could see another callbacks. Even you could define your custom callback in Keras. Okay, now the second epoch's done. Let me to refresh this page. Okay, that's it. Now you could see that we have a very good accuracy, 97% on training data and 98% for test data, which is pretty good. I think now you know how to create the models in the Keras. Actually, we will see lots of other things later in Keras, and the good thing about Keras is that it is very simple to build your models in that, and so you don't need lots of effort to do that. So I hope you enjoyed from this session. If you have any question, please contact me through the Slack channel and ask your question there. So hope to see you in the next session. Bye.